Welcome back. In this lecture, we are going to talk about integer linear programming. The main objective of this lecture is to differentiate real linear programming versus integer linear programming. Okay? And we will talk about the difference that treating the variables as reals makes from treating the variables as integers. Okay? And it's a big difference, and we need to understand this difference. Linear programming will offer the first part of this class. It will take up the first part of this class. In the second part, we are going to talk about integer linear programs, but it is good to understand upfront what the difference between the two programs are. Okay, so recall what a linear programming problem is. So a linear programming problem with decision variables x1 through xn is written like this: max c1 xn plus c1 xn subject to some linear inequality constraints. So we will note that there are many formulations of the linear program, and we are just using one formulation for convenience. Shalom in his lecture is going to talk about some other equivalent formulations that you can reduce the linear programming problem to. The feasible region is an n-dimensional polyhedron, which means that if you take any inequality here, okay, you get a straight line and everything to one side of a straight line. And this kind of region in geometry is called a half space. Okay? And therefore, the feasible region of a linear program is the intersection of m half spaces, because there are m constraints here. Okay? And this region is called a polyhedron. Okay? And this is n-dimensional because there are n variables here. Okay? And there is an implicit assumption which we haven't stated so far, but we have just made it so far, is that x1 to xn are real valued variables. What that means is every point in the feasible region is a possible solution to the linear program. Okay? And therefore, x1 to xn have been implicitly assumed to be real valued variables. All right, so we can relax this assumption, and suppose we assume that x1 through xn are integer valued variables. Now, what's an integer? Let's recall that integers are the set of negative and positive numbers. Okay. Now, in some situations, it's very natural to assume that a decision variable takes on integer values. One such situation could be if a decision variable corresponds to the number of people. Okay. Maybe the number of people that you allocate to a particular task. And in such cases, you want the decision variable naturally to take on integer values as opposed to real values. In some other situation, a decision variable can mean, if it's 1, it means you do something, and if it's 0, it means you don't do something. And in those cases, an intermediate value of 0.5 doesn't help you make a decision. So you are interested in it being 0 or in it being 1. And those are also cases where you would like your variables to take on integer values rather than real values. Okay, and the 0, 1 you would like to enforce using a constraint like saying 0 less than equal to xn less than equal to 1. But you do not want values like 0.5 or 2.5 or 3.75 or pi or e. Those are values which do not make sense in your problem. And in those cases, you want to enforce additional requirement that the variables, the decision variables in your LP, be integers. Okay, and that changes the nature of your linear program from a real valued linear program to an integer valued linear program. So a linear program by itself suggests a real linear program, and the real is implicit. Whereas when you write down an integer linear program, you are saying that all the variables in the linear program are interpreted to be integers. Okay? Now there is an intermediate case called a mixed integer linear program. Okay? And in the mixed ILP case, some variables are integers and some variables are reals. Okay? But in this class, we are going to look at ILPs and LPs as integer linear programs and real linear programs. We will give you a brief description of how to solve mixed integer linear programs. But if you understand this and this, then MILPs are kind of easy to understand. Okay? Now, what does the feasible region of an integer linear program look like? We saw what the feasible region of a real linear program looked like just 2 slides ago. And in this case, I am going to make this linear program an integer linear program by telling you that x1 through xn are integers. Okay? Now, you still get that every constraint gives rise to an inequality. Okay? But you're no longer interested in the half space, but you're only interested in the integer points in this half space. So I wrote down this region, and I made lots of points here, and each of these points is an integer point. Okay? And we are only interested in the integer points in this half space and not every other point. Okay? That's what this says. X1 through Xn are integers. And the feasible region therefore becomes a Z polyhedron. It's not the entire green region. It's the black dots that are inside the green region. And that's a very important observation. It changes everything when you go from real linear program to integer linear program. So to recap what changes, and we will look at this in great detail as this class progresses, just to give you a quick recap of what changes. Linear programs are polynomial time problems. What that means is we have efficient algorithms that can solve linear program in time that's polynomial in the size of the linear program. And this is a very deep result in linear programming. We will not have time to go through this entire result in this class, but we'll give you an argument for why this is true. And what this means is you can solve linear programs with as many as 10 to the 5 variables and similar number of constraints. And if it's sparse, you can go even further to 10 to the 6 or 10 to the 7, which means you can solve linear programs with millions of variables under some assumptions. And it's possible to do so. Integer linear programming, the moment you restrict the variables to integers, then your ability to solve large problems are curtailed. So solving integer linear programs with hundreds of variables or thousands of variables is considered really challenging. It's considered beyond the reach of what can be done with current solvers. If the higher you go, it gets exponentially harder with the current algorithms. Current algorithms take a lot of time, and the amount of time they take goes as 2 to the size of the problem. Whereas in linear program, they go size of the problem to the power of some constant, like 12 or something. So this can be solved for much larger instances than this with existing algorithms. Okay? So the question really arises is, are there going to be efficient algorithms for integer linear programs versus linear programs? Which means, can the difference between ILPs and LPs be negated by finding a very clever algorithm? And the answer is it's unlikely. And that's because integer linear programs belong to this class of problems that we in computer science we call NP, standing for non-deterministic polynomial time. And real linear programs belong to this class. Okay? And the question is, can integer linear programs be solved with the same complexity as linear programs? Changes to the P equals NP question, which has been open to date for nearly 50 years. It's not quite been 50 years yet, but it's soon going to be 50 years for which the problem's been open. And the Clay Math Institute is willing to give you $1 million or more for answering this question. And society as a large is going to think of you as the next big genius, someone who's even bigger than Albert Einstein, if you can solve this problem, because the impact you will make on society is going to be big. And by solving this problem, you can provide either answers. You can say for sure that integer linear programming is different from linear programming. The exponential complexity is unavoidable. Or you can say integer linear programming is in the same complexity class as linear programming, which means ILPs are also in polynomial time. Okay, and either answer is going to win you $2 million and change the world of computer science as we know it. That's why this is really important for us. Okay, so let me give you a couple of illustrations on the difference between ILP versus LP. Let's take the example problem that we have. And we have seen this problem before, and we have solved this problem. We found optimal solutions, x1 equals 6 and x2 equals 11. Okay? And the optimal solution is right here, and this is the direction of the objective function. We saw this in the first lecture. Okay? Now, this is the optimal solution for the real valued linear programming. Question is, if you change x1 and x2 to be integers, does the answer change? Okay? And if you think about this for a minute, you will find that the ILP in this case, whose feasible region is all the integer lattice points in this polyhedron. Okay, I'm not going to draw them all, but this is also an integer point. Okay, and because this is an integer point, okay, this also becomes the solution for the ILP. And we will go through this in much more detail when we start really talking about solving ILPs. Okay? So in this case, ILP answer equals LP answer. And when this happens, this is something mysterious and really nice that we would like to happen for practical problems, but unfortunately it does not happen. For practical problems, this is still rare. The ILP answer being the same as the LP answer is quite rare. What happens in practical problem is illustrated more by this example. Okay, and in this example, you have the ILP problem to have an optimal solution, that's here, whereas the LP optimal solution is here, and the objective is x2, so the objective direction is like this. You're trying to maximize this, and the ILP answer is 1, 1, the lattice point, and the LP answer, which I won't write down, is between here and here, so it's between 1 and 2. Okay, so this is real valued, actually real valued, and this optimal solution is 1, 1, that's here. Okay, and this makes ILP different from LPs, and understanding this difference is going to be in the second half of the class. So when we proceed, we are going to assume that LP means real valued linear programming and all variables are real valued. Okay, so I'll stop with that and move on to the next part where we will learn more about linear programming. Thank you, and I will see you in the next lecture.